Go.
Hello everyone, I am Janani Rajesh Kumar. I want to start by asking you, what do you think about the electronics that are all around us? Your phone, your laptop, the server farms that power the cloud, they all have one thing in common. They are rigid and they are flat. This is the main problem that we face, and that's why we chose this problem statement. The fundamental rigidity is a major limitation of traditional electronics. The core components like silicon chips and printed circuit boards are rigid and brittle. We have this problem where conductor metals are too brittle in thin films, and while polymers are flexible, they are poor conductors. Even when we try to force these materials into flexible forms, they suffer from mechanical deformations and stresses, leading to micro cracks and a loss in performance. This creates a huge challenge. How do we create materials that are both conductive and stretchable and that can withstand physical stress? The solution then lies in the emerging field of flexible and stretchable electronics. This isn't just a niche area of research, it's a field with significant backing because its application will transform multiple industries. For example, in healthcare, we are developing wearable sensors and electronic skin patches that can monitor most chronic diseases and provide real-time data. Imagine a patch on your arm that continuously tracks your vitals without the need for bulky equipment. We are also seeing major research in soft robotics. To create sensitive robots that can handle delicate items with human-like precision, their skin needs to be flexible yet contain complex wiring and sensors, which is something our problem statement adheres to. Beyond these, flexible electronics can be integrated into unexpected places to enable smart capabilities. From automated inventory management using smart labels to fluid level sensors in bottles for auto replenishment. And in the military, you have applications like smart uniforms with embedded flexible antennas which can monitor a soldier's physical state like dehydration and fatigue. These advancements are not just a possibility, they are even happening right now. The growing demand for wearable devices, flexible displays and Internet of Things applications is fueling rapid progress. This is the main motivation behind our research topic. The future of electronics is flexible and it's a future that's closer than you think.
Hello everyone, I am Aryan Shah and I will be explaining the working principle behind stretchable materials for electronics. Traditional electronics are built from rigid materials like silicon and thin metals. These work very well electrically but fail almost immediately when bent or stretched, usually at strains below 1%. Polymers, on the other hand, are flexible but they don't conduct electricity efficiently. The key principle to flexible electronics is to decouple electrical performance from the mechanical deformation. In other words, the device must still be able to conduct electricity even while it is being bent, twisted or stretched. This is achieved by reshaping conductors into patterns like serpentine lines that can elongate without breaking, and by using soft substrates such as elastomers which absorb the stresses. Thanks to these principles, devices can tolerate strains as high as 10 to 300%, enabling applications such as foldable displays, wearable and medical patches, and soft robotic skills. Now we come on to the mechanisms which enable the flexibility. So to achieve this principle in practice, researchers use a combination of structural designs, new conducting methods, and soft substances. Structurally, nano ribbons, serpentine patterns, and even kirigami style cuts distribute the strain evenly and prevent the fractures from happening. In terms of conductors, silver nanowires and carbon nanotubes are used. They form networks that can slide and maintain conductivity even when the material is stretched. Graphene is also used because it provides both strength and flexibility. And one of the most exciting new approaches coming up is using liquid metals like a gallium indium alloy. These flow and reconnect as and when the material is stretched or twisted. Coming to the last thing, these mechanisms together ensure that electrical performance remains even during large deformations. Now we go on to the scientific principles behind these methods. So the deeper scientific foundations explain why these methods work. Soft materials like elastomers and hydrogels are viscoelastic, which means that they dissipate energy and even cracks from spreading and prevent cracks from spreading, unlike brittle silicon. The next comes the percolation theory, which describes the networks of nanowires or nanotubes continue conducting as long as connected pathways exist. These create redundant pathways which break while stretching or bending. Next is the geometric mechanisms which explain how geometric mechanics explain how serpentine and mesh structures redistribute strain rather than concentrating it. Other key principle is self-healing. So there are two types of self-healing systems: extrinsic systems which release a conductive ink from microcapsules when there is a crack forming, and intrinsic systems which use reversible chemical bonds like hydrogen bonds or disulfide bonds that reform after breaking. Liquid metals also reconnect almost instantaneously because of the surface tension, and hydrogens can reassociate polymer chains to recover both strength and conductivity. Altogether, these scientific principles make it possible for stretchable electronics to be robust, reliable, and suitable for real world use.
Hi everyone, I'm Shashwat Gupta. See, the first common question which comes to everyone's mind is, if stretchable electronics have such potential, then why don't we already have them in our daily life? To answer that, I'll walk you through three big challenges that researchers are currently working on. The first challenge is the stretchability versus conductivity dilemma. Electricity flows best when electrons move through dense and broken paths. Think of a crowded hallway where people keep bunking forward, but stretchability requires pulling the material apart, which reduces those pathways. Look at the image. The red lines represent conductive nanowires inside a rubbery wave. When relaxed, they form a dense network. But when stretched, the network is literally pulled apart. Connections break, resistance rises sharply, and eventually the material stops conducting. So the very property that makes materials flexible works directly against its ability to carry current. The second challenge is fatigue and durability. Even if a material stretches and conducts at the same time, will it last after thousands of uses? Think of a paperclip. Bend it once, fine. Bend it back and forth, it weakens and eventually breaks. The same thing happens here. Repeated stretching causes micro cracks in the conductor. The rubber base deforms permanently like an old waistband, and layers can peel apart. If you look at the graph, you can see how property degrades over cycle. Initially we don't see anything, but after 20,000, 40,000 cycles, we see that the materials start degrading. Finally, even if we solve conductivity and durability, there's still the problem of the power. Stretchable electronics need stretchable power sources, but the batteries are notoriously difficult to manufacture. There are three main issues which comes while manufacturing batteries. First, the mechanical issue. When stretched or bent, battery layers can peel apart, creating weak spots. Safety is one of the bigger concerns, where conventional batteries use toxic chemicals, and if there is any leakage, this might be of huge damage to skin. Low energy density is one other issue, where flexible batteries simply can't store as much energy. A lot of their volume is taken up by non-active stretching material, so they can't hold as much power as compared to our rigid phone batteries. This image illustrates a bend in the battery, where we see the initial part, the upper part is under tensile stress, whereas the bottom part is under compressive stress. So once these three challenges are overcome, we'll move to a future where electronics are as flexible and as resilient as our skin.
Hi, I am Palash. Today I'll be talking about the emerging breakthroughs in stretchable electronics, focusing on power sources, conductors and semiconductors. Let's begin with stretchable power sources. A key challenge for wearing systems has been integrating safe and reliable energy storage. Conventional lithium-ion batteries are rigid, cytotoxic and thermally unstable, making them unsuitable for conformal applications. Recent research has introduced hydrogel-based electrochemical cells that are flexible and self-healing, retaining nearly 90% of their capacity even after mechanical damage. Although their energy density is somewhat lower, their safety and resilience make them ideal for next generation devices. Parallel advances in stretchable or organic photovoltaics are equally exciting. Polymer active layers can now sustain over 40% tensile strain with negligible performance loss, and some prototypes even achieve reversible elongation up to 300%. This positions them as excellent body conforming energy harvesters. Moving to stretchable conductors and electrodes. Traditional indium tin oxide suffers from fracture and high cost under strain. Materials like graphene, metallic nanowires and conducting polymers now offer high conductivity with mechanical compliance, enabling robust, scalable optoelectronics. Liquid metal composites go a step further, remaining electrically stable under deformation and even providing electromagnetic shielding, ideal for antennas and interconnects. Finally, flexible semiconductors and substrates are enabling complete stretchable systems. Silicon nanoribbons preserve electronic performance while remaining flexible. Metal oxide semiconductors can be processed at low temperatures on soft substrates, and new biodegradable and recyclable platforms are paving the way for sustainable, eco-friendly electronics. Together, these breakthroughs are rapidly moving stretchable electronics from research labs towards real-world development.
Hi, I am Venkatesh and I am going to talk about future trends. Today, I want to talk about the future of a field that's set to transform our world, flexible electronics. Forget the rigid, bulky devices of the past. This technology allows electronics to bend, fold and stretch, and its potential is immense. The global market, valued at $29.4 billion in 2024, is projected to more than double, nearly $71 billion by 2032. That's a massive, impressive growth. The biggest driver of this expansion is the display segment, fueled by the demand for flexible OLEDs in devices like foldable and rollable screens. So, what's making this possible? The key is in the materials. Researchers are moving beyond traditional silicon and exploring next-gen materials like 2D nanomaterials such as graphene and even liquid metals. These aren't just for flexibility, they have remarkable properties that allow electrical pathways to self-heal, repairing themselves under mechanical stress. This means devices can be incredibly durable and reliable. Another breakthrough is in the manufacturing. Scientists are now using complex 3D printing techniques to directly draw electronic circuits onto flexible substrates like fabrics. This is leading to revolutionary applications like smart textiles for military uniforms or sports equipment that can monitor performance and even health. Now, let's move on to some incredible real-world projects. Samsung and LG Display are the forefront with prototypes like LG's stretchable OLED screens that can stretch and contract without any visual distortion, paving the way for foldable phones and wearables. In healthcare, Flowzonics Medical has developed the Flow Patch, a wearable ultrasound device that can non-invasively monitor blood flow, replacing bulky hospital equipment. At the University of Chicago, they've created a hydrogel semiconductor, a soft tissue-like material that can seamlessly interface with the human body, which is a major step forward in the next-gen biosensors and brain-computer interfaces. At Virginia Tech, researchers are pioneering the use of liquid metal microdroplets to create soft self-healing connections for advancements in soft robotics. The future is not just flexible, it's also intelligent, integrated, and incredibly responsive. This field is set to blur the lines between technology and the physical world, creating a future where our devices are as adaptable as we are. Thank you.